All right, grade 12s, we're on day 6 of exponential functions. The title's a little bit ominous. It's really solving real-world problems. And we are doing algebra and TI-83s to do it, but this stuff should be a little bit practical. Following on the money example that we did yesterday, we have a long-term investment of $1,000 and it's at a fixed rate of 8%, which would be really nice. You can't get that anymore. But we want to know the value after 8 years. So an exponential equation, because it's compound interest, would be initial value, the rate of growth, which is 8%, to the power of the number of years that we would add this interest over and over. So if we know the value at 8 years, this is an easy thing to solve. We put our value of 8 in for the exponent and just type it in a calculator. We have $1,850 and 93 cents. So if I asked you for the interest, it would be $850.93. So when you know the exponent, the operation is easy. We want to know when is the value $2,200. This is a harder problem. We have 2,200 equals 1,000. 1.08, and we are solving for x. We can do it algebraically or using a graphing calculator. Well, algebraically not so much. I suppose we have guess and check at this point. Or we can use a calculator. If I know that in 8 years the value of that investment is 1,850, then it's going to be a couple years down the road that I would have the value of 2,200. So I'm going to guess that x would be, let's go with 12 years. So the amount is 1,000 times 1.08 to the 12. Let's see how close I am. I would get 2,518 and 17 cents. So that's too high. 12 years is too far. Let's go right in the middle. Let's look if x is 10 years. The amount would be $1,000, 1.08 to the power of 10 times 1.08 to the power of 10. $2,158.92. So not large enough. So it's between 10 and 12 years. It's closer to the 10-year mark than it is the 12-year mark. So let's go with 10.2 amount. 1,000. Oh, I did a 10,000. That'd be better. 1.08 to the power of 10.2. 2192.41. Very close to our 2,200. So about 10.2 years. Let's have a look at our graphing calculator. There, it's hard to see it all at once, but we have our first equation would be, when is this investment, so our 1,000, 1.08 to the power of x, and I want to find its point of intersection with the line y equals 2,200. Now I know I'm going to have to adjust my windows for this. I know that time is going to be more than 10 years. So I'm going to make that x max. Let's go with 15. And I'm talking about a decent amount of money. So in the thousands for sure. 2,200, so I'll make it 3,000. Let's see if we can find the point of intersection now. I have a strange feeling I did something wrong. That looks like a straight line. Yes, I did. This is to the power of x. Silly me. So insert power of graph. This should look, there's an exponential look. And where it intersects, 2200, point of intersection is number 5. Enter, enter, enter. Okay, let's see what we got. 10.2 years, 10.24, so almost a quarter of a year, so 10 years and 3 months. If you're going to tell your client, 10.24 will give you your $2,200. Second problem, the population of Alberta can be modeled by the equation p equals 2.28 times 1.014 to the n, where n is the number of years since 1981. When will the population reach 4 million? So I assume that the population is in millions. N is the number of years since 1981, and I want to know when it reaches 4 million. Okay, so I want to find when 4, 2.28, 1.014 to the n. My two options at this point are guess and check and graphing. With guess and check, I would put values of n until I get as close as possible to 4 million. So let's try, if it's 2.28, let's try 20 years. So in 20 years, the population is 2.28. So it's only got an increase of 1.4%. And if we type that into a calculator, I get an answer of approximately 3.01 million. So I'm not to the 4 million yet. Let's go 30 years. So the population in 30 years is 2.28, 1.014 to the n. And we'll get 3.46 million. One more, n equals 40 years. 2.28, 1.014 to the 40, which is about 3.98 million, which is really close. Okay, let's verify that with the graphing calculator. So I am looking for the point of intersection where our population equation, 2.28 times 1.014, 1.4% to the power of x meets the line of 4 million. Let's see if we can see it. Okay, it took a minute there, but there is our graph. We cannot see the point of intersection, but we can see that there's going to be one further to the right. And we know that our answer, because we've already done the guess and check, is past 40 years. So let's make our x max 50. We don't need any more y values. We can see that just fine. And here is our exponential curve. And here's our line. We can see that point of intersection, though not clearly. The graphing calculator can find it. First curve jumps to the second curve, enter. 40 and a little bit. So the point of intersection, 40.4 years will give us our 4 million. Before we work on our homework, I'd like to do one of them with you. So page 73, number 5. I don't think you have space for this, but it was the first question I was going to assign you for homework. We're given a table of values, and we're asked to predict when this person is going to make a certain amount of money. So we want to solve an exponential equation, and we've got tools to do that, but we need to use the table to find the equation first. So we have Taylor earning money over a period, and you can see that it's going up rather sharply. So let's look at the first differences first of all and see what we've got. If we subtract to get our first differences, let's grab a calculator. The first one's nice, 6650. 8350, take away 6650 is 17. $17.5. Oh, I can't do math here. This is 16, 50, 17, 17.5, 19. Take away 18.03. So I can see this raise in this earnings does not go up as a linear function. I'm going to look at the ratios of the first differences. So I am doing 17 divided by 16.5. 17 divided by 16.5 is 1.03. So my ratio between those two is 1.03. So it's going up by 3%. 17.5 divided by 17 is 1.03. If you round just a little bit, 18.03 divided by 17.5 is 1.03 approximately again. So our rate of growth using that table of values is 1.03. Let's make our initial value 550, so this is earnings, and our time is going to be since 2004. And let's make our time t. Initial value times the rate of growth, 1.03, to the time, year since 2004. There's our equation, and we want to know Taylor's weekly earnings in the year 2012. So for B, I need to know my t value. The time for 2012 is how long that was since 2004, which would be 8 years. So my earnings in 8 years would be 550, 1.03 to the 8. 550, 1.08 to the power of 8. Nope, I gave her a really good rate of increase there. 1.03 to the power of 8 is 696.72. C asks us to predict when she might expect to earn more than 850. So we are solving the equation, when is 850 equal to her earnings? This would be hard to solve with guess and check. I would use a graph. Our two equations would be, come on, turn on for me. There we go. First of all, our earnings equation, 550, 1.03 to the power of x. And our second equation would be the line, 850. We need to adjust our windows. If it can stop for me for a second. Our windows need to make sense with the problem. We don't need negative values at all for x really, but our time is the year since 2004, and we're not looking very far into the future. That's more than enough. Our y maximum, we're talking money, so we need thousands of dollars. Probably. So there is her increase in earnings. And there is that line. So we can see the point of intersection. The graphing calculator can find it for us. Whoops. At 14.7 years. Comma 850. She can expect to earn $850 when she's over halfway through her 14th year. So let's go back and have a look at your homework. We have done number 5, and I have graphing calculators.